Okay, we are back at it, deep in the VSEPR theory. We're going to finish this up by talking about 5 and 6 electron groups as we wrap this up. Okay. Remember, we're thinking about geometry of stuff. Remember, electrons want to be as far away from each other as possible. This gives us valence shell electron pair repulsion. That's what VSEPR theory stands for. Um, as we do this, again, I'll be using the simulation as we go. Remember, we want to be able to count electron groups. So remember, what are electron groups? Lone pair, a single, a double, or a triple. Each one of those things counts as one, I almost said lone pair, one electron group as we do that. Remember, we got to have a good Lewis structure. And we're going to think about things that have 5 and 6 electron groups, which means by necessity, all of the central atoms of this are going to be violating the octet rule, and that they're going to have more than 8 valence electrons when we do that. Because if we have 5 electron groups, then that's going to be 10 electrons. And if we have 6 electron groups, it's going to be at least 12 electrons. Okay. We're in this class not going to deal with more than 12 electrons, more than 6 electron groups. But it is theoretically possible with bigger central atoms to have bigger geometries and more things there. Okay. We're just not going to talk about it in this business. All right. When we're talking about 5 electron groups, it's trigonal bipyramidal. And I really should have this animated so it wasn't all here all at once because it's stressing me out. But doesn't matter. For 5 electron groups, what we're thinking about is something called trigonal bipyramidal electronic geometry. Okay. Um, and this is hallmarked by having, it's a lot like the trigonal planar. Okay. If you look here, there's a trigonal planar setup in the center, right? There's 120 20-degree angles in the center to make a triangle. Okay. And then there's one on the top and one on the bottom. Okay. So that's our 5 electron groups. We're talking about PCl5 right now. If you're going to draw a Lewis structure for this, you'd probably draw something starfishy. I am not going to put the lone pairs on the fluorines because no one wants to see that. Okay. Here we go. So it doesn't matter what your Lewis structure looks like. You want to be able to count 5 electron groups. Oftentimes when you draw this with wedges and dashes, you'll put phosphorus in the top, the 2 axial ones this way. I'll explain axial and equatorial in a second because I realize I didn't do that yet. And then you'll have one on a wedge coming out and one on a dash going back. Excuse me. Okay. Remember, I'm not going to ask you to draw stuff in wedges and dashes, but we want to be able to recognize what the wedges and dashes means. Remember, the wedges are coming at us, towards us, and the dashes are going away. Okay. If your thing, compound, molecule, whatever, doesn't have a lone pair on the central atom, then your geometry and your shape are the same thing. And so your trigonal bipyramidal and trigonal bipyramidal. Let me get a better drawing for us here. I think PCl5 isn't even one of the things. Haha, yes. Okay, PCl5. This is nice. So here you can see it, if we look at it this way, this is the trigonal planar center of it, right? 120 degrees around the middle, okay? And then there's one pointed at us and one pointed backwards. If we turn this around this way, then what we see is, okay, the middle, this is the planar. We're looking at it, this way. I don't know if you can see my hand, but this way. And then we have the line through the middle, the top and the bottom that way. Okay. Now the sticky part about these trigonal bipyramidal is that there's 2 bond angles in here. Okay. Around the center in the trigonal planar area, they're all 120, just like in trigonal planar. That's why this works well. But between the plane and the edge ones, they're all 90 degrees. Okay. So it's a little bit different than other ones we've looked at. Okay, turn it this way, kind of make it look all fun. Let's go back to the picture here. Okay, so the angles around the center, so here are 120. The angle between the top and the bottom are there. Because we have two different angles, we can locate two different, I say two different types of chlorine or whatever central outer atoms in here, but we can find two different things. The equatorial ones are the ones that are part of this trigonal plane in the center. Okay, because equator runs around the center of the globe, so it makes kind of sense to do it that way. The other ones are axial, and they're axial because they're along the axis around the middle. So there's the axial ones and there's the equatorial ones. Okay. When we start thinking about replacing these atoms with lone pairs to make the other geometry shape options, okay, um, in the trigonal bipyramidal case, the lone pairs are always equatorial. Let's write that down. Lone pairs on the central atom go equatorial. Okay. So when we're looking at SF4, okay, SF4, it would be so nice if it were tetrahedral. I'm not going to draw the lone pairs on the fluorines again because, gosh, okay. But we do this, and then it has one lone pair. So we can put the lone pair in the center. So that's still 5 electron groups there. The lone pair goes in the equatorial spot, not in the axial spot. Okay. It goes equatorial because the equatorial spot has more room for it. Okay. Or one way to think of it is it has fewer bad interactions with the lone pairs on the fluorines. Okay. But there's just physically more space around the equatorial one. Okay. So with SF4, we give this a fun name, seesaw. You can't really see it in the model they've drawn here, but you can see, it's leaning on the triangle part and the flat part goes across. If we flip back to our model and say, please tell me SF4 is here. Yes. Okay. So there's a seesaw part. See, this part can go down and this part can go up, all that stuff. I know, I'm just being silly, but you'll notice the lone pair is in the equatorial position. Our axial fluorines are still there and everything is still fine. Okay. You can always make it so 3 of the things touch. Okay, but you can't make it so all 4 things touch. All right. Now, 5 has a lot of options. So we can get trigonal bipyramidal with no lone pairs. We have seesaw with 1 lone pair. You can also have 2 lone pairs, in which case you're going to occupy 2 of those equatorial positions. So you're going to get rid of this one and you're going to get rid of that one. I don't know why I did it with blue, whatever. Okay. And that ends up being T-shaped because you're left with just the axial ones and then one of the equatorial ones. Okay, BRF3 is a good example of that. And if you go with XEF2, then you have something that's linear because you've taken up all 3 equatorial spots with lone pairs. Okay, I'll just do a quick rundown on this. I don't think these are here. Nope. Okay, back to the model. Okay, so BRF3 has 3 atoms and 2 lone pairs. Okay, so those angles are 90 degrees. The 2 lone pairs are part of the equatorial one. Okay, and this is T-shaped. If we take out one of the atoms and replace it with a lone pair, okay, now we're linear. Those 2 things are 100 degrees from each other. The trigonal planar triangle in the center is now all lone pairs, and the 2 atoms attached are 180 degrees from each other. Okay, let's go back to this. Those are our sets of 5s. Okay, if we're looking at 6 gets a little bit more complicated, but it's a little less complicated actually. There's fewer options that we're going to talk about. All of the bond angles are the same. So all of our angles are 90 to are 90 degrees. Okay. And now we have 4 around the center and 1 on the top and 1 on the bottom. If all 6 atoms are identical, you cannot tell the difference. So there's not really equatorial and axial here because all the bond angles are going to be the same. Okay. If we're going to draw this with wedges and dashes, you know what? Yes, I want to keep this. I'm just going to throw in a blank side so I can draw something without having to be small. All right. So if we draw this with wedges and dashes, we had SF6, but sulfur, come on, man. Sulfur in the center. You can draw it flat with just lines coming out, but if you want to see the wedges and dashes, this is how we should do it, right? You're going to have 2 that are up and one up, 1 down. You're going to have 2 wedges coming at us and 2 sets of dashes going behind, okay? And then each one of those will have a fluorine on it, like so. Okay. I will have you draw octahedral stuff with wedges and dashes when we get to Gen Chem 2 and talk about metal complexes, but for Gen Chem 1, we're not going to draw it. I want you to recognize it though. Remember, those fluorines on the wedges are pointed at us, and the ones that are on the dashes are pointing away. Okay. Let's go back. When we're replacing an atom with a lone pair in octahedral, if we put 1 lone pair there, so BRF5, so there's a lone pair right here. Okay. The lone pair can go anywhere. We typically draw it pointing down, but you can draw it however you want to draw it. And any one of those positions is fine. Okay. It needs more room. We could draw it with our wedges and dashes if we're so inclined. This breaks my good rule of thumb of saying have as few wedges and dashes as possible, just because we're trying to illustrate that it is square pyramidal. Square pyramidal because it's a square-based pyramid, if you will. Okay, so it looks like that. When you're put on the next lone pair, so if you have octahedral, but you have 2 lone pairs there, it becomes square planar. Because remember, those electrons need to have as much room as they can. Okay, so it wants to be as far away from those other lone pairs as it can get. So the first one can go anywhere you want. The second one, so if this one was the first one we did, the second one has to go in directly opposite that. Okay, so you have 1 on the top and 1 on the bottom, and that makes everything left over is in the plane of itself. Okay, let's take a quick look at some of these here. Let's take out these lone pairs. So 5, 6. Okay, here's our plain old octahedral. Everything is 90 degrees. If we take out a bond and put a lone pair there, this is our square pyramidal. Trying to get that lone pair to point down. Sorry, there we go. So a pyramid with a square bottom. Okay, and if we take out another lone pair, no, take out another atom and add a lone pair, notice the lone pair ends up opposite of its friend there, and we have a plane of square, and the lone pairs are along the axis. This one, for square planar, you don't have to draw it with wedges and dashes. Technically, you can. If you draw it as wedges and dashes, it's like you're looking at it this way. If you can just draw it with 4 lines, you're looking at it this way. Okay, those are really the only octahedral options we're going to have. You might see some things that say you can have linear or T-shaped for octahedral as well, but those things are less common and we're not going to stress about them. Okay. All right, so for our square planar, we could just say XE, F, 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 and of course you'll be putting lone pairs on these fluorines as needed. Okay, to summarize up things here, maybe. I've lost my, there we go. Shoot, just stab me in the face, not doing a PowerPoint correctly. All right, these are two summary nice tables, just from two different books. I couldn't decide which one I like better. I like this one on the right because it has colorful examples. This one on the left has generic examples, but they're both reasonable and they give us the same information. Okay. Every electronic geometry has several molecular geometry options. Okay. These are all the ones that we're going to talk about. These are the only ones we're going to test over. You'll get this as a handout as needed. Um, these are two fun graphics I found um, to help if you want like this. These are linked on our Blackboard page as well. Just remember, we're not talking about things that have 7, and we're not doing T-shaped octahedral things, right? So we're not doing these guys either. Okay, they do exist, but they don't exist in anything that we're going to talk about. Okay, so get your good Lewis structure, count your central atoms, and know what the names of the shapes are. Okay, and spelling matters. I'll catch up with you later. Have a good one. Let me know if you need me or have any questions. See you next time.